Hello, my name is Georgi Radulov and I would like to welcome you to my podcast about the current mirror OTA, where OTA stands for Operational Transconductance Amplifier. So, this architecture that we will discuss looks like two-stage, but actually it behaves like a single stage. So, let's see it. This is the architecture. And what we have here, we have the input pair transistors, which transform the input voltage into currents through their GM. Then we have a current mirror here, hence the name current mirror OTA. The currents from the input pair will be mirrored into the output. Here the current will be mirrored here, and then from here with this current mirror will be mirrored at the output. So let's analyze how it works. So at the output the currents will be transformed to output voltage. So first the biasing conditions. We have a biasing current source that is dumped in a diode connected transistor. So this current supplied from outside gets into this diode connected transistor, and for this transistor to be able to conduct this current to ground, it will have to adjust its gate source voltage to the required value so that this current can flow through the channel, drain source channel. So depending on the size of the transistor, the voltage, gate source voltage, will be automatically adjusted. Now this gate source voltage is actually shared with this transistor. So these two transistors construct a current mirror, and then this bias current will be copied here. So these transistors are identical, the input transistor of the current mirror and the output transistor of the current, which is the tail current. Hence, this current bias current will be copied into the input differential pair. We call this the tail current, which will be equal to the bias current. So this will be the tail current of the input differential pair. If the inputs are balanced, so this input is equal to that input, then this current, the tail current, will be split in two. Hence, half of the bias current will go in this branch, and half of the bias current, the other half, will go into this branch. Then this current will go into these current mirrors, which have ratios of 1 to 2, and this can be seen from here, from these GMs. And then this means that this current will be copied into the output with a ratio 1 to 2. So here we will see actually the bias current. The same operation happens with this current, which comes into this diode connected transistor, which adjusted its source gate voltage so that it can conduct this current. This source gate voltage is shared with this transistor, which is the output transistor of the current mirror. This transistor is 2 times bigger than this transistor, so the ratio 2 to 1. And then this means that this current will be copied here with a ratio 2 to 1. And hence we have the bias current here. So this is the same current as here. Again, we have a current mirror, and this current mirror will copy this current simply here. So here from the top we will have the bias current, and here we will have the bias current flowing to the ground. So the output stage here, the two transistors are balanced. Then let's analyze further this architecture and try to get its main property, one of the main properties, the static gain. So the static gain is defined as the output voltage against the input voltage. Now the input voltage is differential, we have a differential input pair, and the output voltage is single-ended. Hence the gain, static gain, will be the output single-ended voltage minus the input differential voltage, and the differential voltage of course is V in minus V in minus. So let's see how this works. Let's suppose that we have input voltage which is delta V in. So sorry, something's this is V out. Yeah, because this is differential, input half will be applied here, the positive input, and the other half will be applied at the negative input. If you subtract these two, you'll get directly the delta V in. So you provide half of the delta V in here and the other half there with the opposite signs. These input transistors and MOS transistors will transform the voltage, the input voltage, into currents through the GMs of the input transistors. If you apply here certain voltage in this direction and here another direction, in the middle this node will not change in voltage because it is in the middle. Hence you will increase by delta V in this VGS and you will decrease by delta V in half this VGS. This means that starting from the bias conditions, the bias currents as they flow, this current flowing in this direction will get a little bit bigger because this VGS is bigger, and this voltage and this current starting from the biasing condition half I bias will get a little bit smaller. So this is the reason why I drew it in the opposite direction. So there will be small signal currents imbalances in the input stage, which will increase a little bit this current in this branch and will decrease a little bit the current in this branch. The sum of the currents will stay the same, equal to I bias. This is the tail current. Now these currents, these two currents, will be copied through the current mirrors. So we'll see the same small signal imbalance here at the output, but multiply by the coefficient of the current mirror, 1 to 2. So we will lose this 1/2 here. In this branch it will happen the same. So in this direction the current will be copied from here to here, and will also modulate the current in this branch, and it will be GMN delta V in because of this coefficient. This current will be copied with a ratio 1 to 1 by this current mirror, and we'll see this current appearing at the output branch. So now from the top side we have a current that is increasing, and from the bottom side we have a current that is decreasing. Then what happens? How come? We can draw the equivalent circuit of the output stage of this branch. So what we see? We see a PMOS current source, this transistor, which we draw as a current source. Then in parallel we'll have its output resistance due to the channel length modulation of the PMOS transistor. R out. P. We will have absolutely the same here for the NMOS transistor. Then this current source, small signal current source, supplies this current. And this current in this direction is this current. The difference of the currents is this and will flow through the output resistance of the output node. And the output resistance of the output node is constructed by the two output resistances which are actually in parallel. So if you look from this node V out, what you see to ground are these two resistances. So from V out to ground you have two resistors ROP and RON. Hence the total resistance at this node, equivalent resistance or R out, will be ROP in parallel with RON. So R out, I can write, is actually ROP, so it will be this thing here, will be RON in parallel with ROP. This means that this imbalance in the currents, or the excessive currents 2 times GMN delta V in, will be translated into output voltage, delta in the output voltage, through the output resistance of this node, of the output. So the current, excessive current, times the output impedance will be the change in the output voltage. Hence now we can derive the gain. We got an expression for the V out in as a function as delta V in, and if you substitute you'll get 2 times GM R out. Let's recap. This imbalance in the currents is copied to unbalance here. This current is copied here, and this current is simply GM and delta V in, and this current is the same, so the difference of the two currents is 2 times GM delta V in, and it is translated into a change of the output voltage delta V out through the equivalent output resistance at this node. And the equivalent output resistance at this node is the output resistance of the PMOS transistor in parallel with the output resistance of the NMOS transistors. Keep in mind that we talk about small signal output resistances. So this is R out, this is the GM of the input transistors, and this too is due to this current mirror. So this is the static gain. Now let's consider the poles. What are the poles in this circuit? So every node in the circuit, we can associate to every node in the circuit a time constant. A time constant is the equivalent resistance of this node times the equivalent capacitance of the nodes. So here are the nodes, the important nodes in the circuit, and let's consider these one by one. So here at this node, which is this node, there will be a time constant tau1, which will determine a pole P1. The pole will be 1 over the time constant. So let's see the time constant. So it will be the equivalent capacitance that we have at this node, and the equivalent capacitance, you just sum up all the parasitic capacitances that you see here, and you consider also the bulk. Doesn't matter, say just the equivalent capacitor is C1 times the equivalent resistance. Now, what is the equivalent resistance here? What we see is that we have a diode connected transistor. Yeah, something like this. We previously derived that the impedance of a diode connected transistor, so R equivalent, is actually dominated by 1 over the GM of this transistor. So this node, the resistance of this node will be given by 1 over GM of this transistor. And this will be a small value, 1 over GM, because GM is usually a large value. So nothing to compare with the kilo ohms of the output resistance. So this means that the time constant associated with this node, T1, will be a short time constant, or it will create a high frequency pole. Now, what does this mean? We have a time constant, and when we have a change in the voltage, certain capacitance C1 will have to be charged through certain resistance, so in this case 1 over GM. The product of these two defines the time constant. If the time constant is short, we can charge this capacitance faster. If the time constant is long, we will charge the capacitance slower. The time constant will be short if the resistance is small. This means that we charge a capacitance through a very small resistance, so we can charge this capacitance with a lot of current. Hence, the capacitance will be charged quickly. If the resistance through which we charge the capacitance is big, then we will charge the capacitance with a smaller current, which will mean that it will take more time for this node to change its voltage. Hence, the time constant is long, which corresponds to a low frequency pole. So in this case, we can charge the equivalent capacitance here at this node quickly, because we are charging it through a small signal resistance, and its small signal resistance is actually 1 over GM, the small signal resistance of a diode connected transistor. And this is a small value, since GM is in the transistor in saturation is a large value. The same reasoning for this node. This results in a time constant which is also short, hence it will generate high frequency pole. Usually the high frequency pole will be then so high that it will be beyond the unity gain bandwidth of this amplifier, and it will not be dominant. It will not cause problems in terms of stability if we use this amplifier with a negative feedback. Now we have also this time constant here, tau 3, which is actually a common mode time constant. For differential signals, when these signals, input signals, change in the opposite direction, this node does not change. It is in between. Since this node does not change, we don't have a signal component there, and it behaves like a small signal ground. Hence, we have no change in tau 3, and we can just ignore it. It will not slow down our signals. Now we have also tau 4 at this node, which is again a short time constant or high frequency pole, because the equivalent resistance at this node is dominated by the output resistance of this diode connected transistor, which is 1 over GM. Now, the last time constant is tau 5. and it is of course the equivalent capacitance at this node C5 times the equivalent resistance at this node. Now the equivalent resistance at this node will be the output resistance of the PMOS transistor in parallel with the output resistance of the NMOS transistor, just like we discussed with the equivalent circuit here. So the equivalent resistance at this point will be these output resistances in parallel. Now, these are the small signal output resistance of the NMOS and the PMOS transistors, which are due to the channel length modulation effect of the transistor. Usually, for transistors in saturation, these are very large resistances. So we are talking about tens or hundreds of kilo ohms. Which means that for the time constant, if you look now at the time constant, so here, what we have is a large value in the order of kilo ohms, and also C5. When you multiply these two, you get a very long time constant, and it will be a dominant time constant. It will create a low frequency pole, and actually this time constant will determine the cutoff frequency of this amplifier. Now what you have to consider here is that indeed we have many nodes in this architecture, but only one time constant is dominant. And this is because only one single time constant is a long time constant. It depends on the output resistances of the transistors and the capacitance. The other time constants are short time constants because they depend, the equivalent resistance for their nodes is 1 over Gm. They are set by the diode connected transistors, and this resistance is small. Hence the time constants are short, and the poles that are associated with these time constants become high frequency poles. Okay, so now let's consider the biasing of this. Let's consider the minimum and the maximum input common mode voltages. So for the input common mode voltages, we consider when the input transistors change in the same way, and the minimum and the maximum voltages are set by the requirements that the input stage should remain in saturation. All transistors in it should remain in saturation. To determine what are the boundaries of the common mode voltage, we will consider the basic definition of for transistors for the transistors in saturation. Now first, the overdrive voltage. It is the gate source voltage minus the threshold voltage of a transistor. It shows how much the input gate source voltage is beyond the threshold voltage of the transistor. In other words, it shows how much the transistor is turned on. So a basic manipulation of this equation will lead to a basic definition of the gate source voltage. Gate source voltage is equal to the overdrive voltage and the threshold voltage plus the threshold voltage. Usually this is the process parameter. It depends on the technology that we use to implement, to realize this amplifier. And this overdrive voltage is a designer's choice. Now in this example, the overdrive voltages are given, so the designer choices, and also the threshold voltages. So now consider here the dot connected transistors. This gate node is connected to the drain node. So this means that the source gate voltage, which we have here, is actually also the drain source voltage. And the source gate voltage can be directly calculated as the sum of the overdrive and the threshold voltage. So it's like 1 volt. So if the source is at 5 volts, then these nodes here will be at 4 volts. Yeah? Then we consider common mode signals, so they change together. Hence, this node C will also change together with the input voltages. Yeah. Now this is 4 volts. As we calculate, now we ask what is the maximum input common mode voltage. How high can the input go so that all transistors remain in saturation? Since we calculated that this is 4 volts, then we start increasing the common mode voltage, this node C will increase. So this means that the drain source voltage of this transistor will decrease. This is at 4 volts and this is increasing. For this transistor to remain in saturation, we require that its drain source voltage is actually larger than its overdrive voltage. The overdrive voltage is given here. So the drain source voltage can be only larger than 0.4 volts in order to remain larger than the overdrive voltage. Which means that this node cannot go higher than 3.6 volts. If this node C gets higher than 3.6 volts, this means that the drain source voltage becomes smaller than the overdrive voltage and this transistor goes out of saturation. So this means that maximum this should be 3.6 volts. Now, if this can be only 3.6 volts, the maximum value of the common mode voltage can be calculated through the gate source voltage of this transistor. So this is 0.4 plus 0.8, this is 0.8. 0.4 plus 0.4 is 0.8. So this node, when this node is 4.4 volts, this node C will be 3.6, and this transistor will be just at the edge of saturation. If we go beyond, if we go above 4.4 volts for the common mode, the input transistor pair will go out of saturation. Now let's train what is the minimum common mode voltage. If this goes lower, 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 what will happen? As this goes low and this goes low, just node C will follow and it will also go low. Now this voltage here should remain always larger than 0.4 volts, because if this node C gets lower than 0.4 volts, then the tail current source transistor will go out of saturation. So if this should remain higher than 0.4 volts, this means that the common mode here should remain higher than 1.2 volts, because we require one gate source voltage, which is 0.4 plus 0.4, for this current to be propagated. Hence the minimum input common mode voltage should be 1.2 volts. Now, what is the maximum output current that this amplifier can source into the load? Now let's consider what will be the condition for us to have the maximum output current. We are biasing here with certain 20 milliamp. If we source all the current here in this direction, we remove the current here, so there should be no current here. We require no current here, we require no current here. This means that we have to put here ground. And then all the current 20 milliamp will have to flow in this branch. So if I have here 20 milliamp and it is copied with a ratio 1 to 2 to here to the output, then I'll have 40 milliamp at the output as the maximum current that this architecture can source. So here it is drawn, and the gate of the negative input I put 0 volts, the other input I put to maximum VDD. So the tail current that flows here, 20 milliamp, will go all through this branch, it will be copied through this current mirror, and I will be able to source 40 milliamps. Here the current will be 0, 0, 0, so no current, and all the current will be provided into the load. In this example, I put as a load a capacitive load. So this was my analysis of the current mirror OTA. Thank you very much for your attention. What the most important thing that we saw is that it looks like a two-stage OTA, but actually it behaves like a single stage. And the reason for this is that we have only one dominant pole, which is the pole associated with the output voltage. It was here at the output voltage. All the other poles, all the other time constants are short or high frequency poles. Hence, this architecture behaves as a single-ended amplifier. Thank you very much for your attention. Bye bye.